Hi everybody. Uh, okay. Today we will move to chapter number 9. Remember, after the midterm, the level, the difficulty of the chapters become heavier and heavier. It become harder. You need to pay more time to study those sections. Okay. And just a reminder. Our final exam is on June 9th. And the last week I will explain those exams. And again, according to the IHP policy, the attendance is the key point to pass the courses. Not only my courses, including all teachers' courses. Attendance, and my requirement besides the attendance, you need to attend 2 exams. Sure, that's the basic requirement. And if you have, sure, next week I will ask you to report your digital notes here. Is it here? Yeah, the basic requirement, your attendance, and 2 exams. And besides that, if you do the sorry, no. Sure. If you do the digital notes, this proportion is up to 20%. And I encourage everyone to do this. Sure, if you have your own website from previous semester, you can continue to use that. Okay. Any question, please let me know. Again, our final exam will be held on here, June 16th, the week 17. Okay. Sure. After the probability, we discussed something about the discrete probability distribution, continuous probability distribution, especially this part that is about the normal distribution. That's the central concept of this study. And the chapter 7, one sample inference. What does it mean, one sample inference? Because we will move to today's work, chapter 9, about 2 sample interference. Okay. Inference. Okay. Maybe something wrong here. Okay. Let me say something about difference between chapter 7 and chapter 9. In chapter 7, one sample interference, it means in I-Yuan with income over than maybe $1 million New Taiwan dollars. You can define it. Generally, we want to know, for example, if I want to sell shoes for male and for female, I need to know the size. How large size are they prefer to wear? For example, I wear my sneakers that is about 27 centimeter. I'm one of the normal distribution, maybe in the center. But you know, some gentlemen are very tall, some gentlemen are not very tall, and their feet are smaller. And you want to know your population. You want to know your target. You want to say, you want to produce, and you want to sell shoes. So you need to pick up some samples. Sure, besides some references, for example, you can select some useful, reliable source of examples. According to my survey, some company or some health exam offer the information about the feet length for males in I-Yuan or in Taiwan. And after our estimate, we plan to prepare to produce to manufacture the shoes of 27 because on the size of 27 centimeter, this population is the most. And how about some shorter guys, maybe 26, 25? If you want to extend your market to boys, not girls, okay, just discussing about the boys. The boys, maybe you to prepare a size about 24, 23, 22. And now you need to know how to do that kind of interference. Okay. After that, you know how to estimate from limited, a little bit, not a big number samples to estimate the big population. That's the purpose. Okay, and now, today we will move to two-sample interference. What does it mean? What does it mean? I select, for example, I continue to the previous example. I want to know the feet length or foot length in Taoyuan from gentlemen, and I want to know the similar situation in Zhanghua or in Taichung, another county or city in Taiwan, whether those men indicated drinking black tea or drinking oolong tea or drinking green tea may reduce the cholesterol level in blood. May, I say may, maybe possibly, okay, I say might reduce the cholesterol level in the blood. But do you have any evidence to say this? One of the simple way is to conduct a two-sample interference exam or the kind of statistic work. For example, I'm a CEO from a food company. We develop a new product about black tea, and we ask some hospital to do the exam, to do the survey. The first group, they drink tap water or to drink just a normal water. But the second group, they drink black tea, maybe 5 milliliters per day. After 1 month or 2 months, we check the cholesterol level. Do they have significant difference? Maybe increase, maybe decrease, maybe. And now we need to know the skills about two-sample interference. Okay, that's one thing. And next, we will discuss something about the regression and correlation. According to my experiences, teaching experience last year, some students think about this part is easier than previous 1, 2, 3 chapters. But some students did not agree with me about this chapter. I have no idea. Maybe you think, oh, it's easy. Maybe, oh, it's difficult. But regression and correlation, this is a still important part for you. Your background is economics and business. You need to know this one. But personally, the principle may be a little bit hard, but to operate it, after running some examples, you will feel, not hard for me. I can learn it. And I think I have no plan to teach about this one, the appendix critical value table. Maybe we can, it's an appendix. We don't need to do that. And now I want to share something about the chi-square and ANOVA test. Chi-square and ANOVA test, believe me, about the principles is very, very hard to understand about chapter 11. When I was a PhD student, I learned the statistics. Wow, it did kill me. But I encourage you that to solve the problems is easy. Because I will prepare some questions similar to our textbook. And sure, please remind me, I will release the auto exam from last year. And I will release the videos to explain I explained how to solve those questions. Is it okay? And I believe that today's week, and we can slow down our steps and say something about this, and enter our final exam. Is it okay for everybody? Okay, and sure. If you think of $1, I need some extra time to study. Can you tell me? Sure. You can go to the biology lab about the building B at 10. Building B at 10. That is biology laboratory. You are welcome to visit me anytime. Okay, let's move to let's move to the chapter number 9. Chapter number 9. Okay, chapter 7 discusses methods for hypothesis tests about one population parameters. Chapter 8 discusses the methods for estimating population parameters from one sample use confidence intervals. And this chapter will look at methods for confidence intervals and hypothesis tests for two populations. And since there are two populations, there are two random variables, two means or proportions, and two samples. Okay, then though with the paired samples, you usually consider to be one sample in pairs collected. Examples where you will do this are: first, testing and estimating the differences in testosterone. Testosterone is a hormone from human body. The levels of men, if before and after they have child, any difference? Because the same man before is one condition, after they have children or child, single or popular, plural or popular. Okay, after they have children, does the testosterone level changes? Yeah, do you have any evidence to show that? Testing the claim the diet works by look at the weight before and after subjects are on the diet. Estimating the difference in proportion of those who approved for President Obama in the age group from 18 to 26 years old and the 55 and over age group. Okay, to check whether they are different. And all these examples of hypothesis tests or confidence intervals for two populations, the methods to conduct those hypothesis tests are the same process. The only thing that changes is the formula you use. Confidence intervals are also the same process, except the formula is different. Okay, let's move to the first section. Section number 1, 9.1, two proportions. Okay, and there are times you want to test a claim about two populations, proportion, or construct a confidence interval estimate of the difference between two population proportions. As with all hypothesis tests and confidence intervals, the process is the same, though the formulas and assumptions are different. The first one, hypothesis test for two populations proportions. Two proportion test. First, state the random variables and parameters in words. X1 equals the number of successes from group 1. X2 number of the successes from group 2. P, it means proportion of success in group 1. P2, it means proportion of successes in group 2. Okay, state the non-hypothesis and alternative hypothesis in the label and the level of significance. The first, the level of significance generally 5%. 5%. Oh, sure, if you have restrict conditions, you can set 1%. It depends on what you need. The first one, hypothesis, P1 equals P2. Or we can say that P1 minus P2 are zero, okay? Alternative hypothesis, P1 smaller than P2 or greater than P2, okay? And the third one, P1 is not equal to P2, okay? There are three alternative hypotheses. Okay, and set and check assumptions for the hypothesis test. A simple random variable size n1 is taken from the population 1. Again, population 1 maybe it has maybe millions of people or thousands of people, but it's impossible for us because we have only limited money, limited talent, limited time. So we need to select samples from the population. And now it's a key point how to select random samples. No bias. Yeah, that's key point. Okay. If N1 is taken from population 1 and the random sample size N2 is taken from population 2, then next, the samples are independent. Okay. C, the assumptions for the binomial distribution are satisfied for both populations. Okay. D, to determine the sample distribution P1 height, you need to show that N1 times P1 equal to or greater than 5, and N1 Q1 greater than or equal to 5, where Q1 is 1 minus P1. If this requirement is true, then the sample distribution of P1 height is well approximated by normal curve. Okay, and next one. Find the sample statistics, test the statistics, and p-value. Okay. Sample proportion, N1, size of sample 1. N2, size of sample 2. P1 height, X1 over N1, sample 1 proportion. P2, X2 over over N2, sample 2 proportion. Q1 height, that is 1 minus P1 height, completion of P1 height. Okay. P2 height, and pull the sample proportion. That is P bar X1 plus X2 divided by N1 plus N2. And the z-score, it looks like this. Sorry, it's not easy for me to read this, but you can check the formula. And usually P1 minus P2, that is 0, since non-hypothesis P1 equals P2. And p-value, this one. Okay, and note. Number 5, conclusion. That is where you write reject non-hypothesis for fail or to reject non-hypothesis. The rule is if p-value smaller than alpha, then reject non-hypothesis. If the p-value greater than or equal to alpha, for example, 0.05. Sure, in this case, it may be used 1%, 0.01. Then fail to reject. Okay. Again, we set alpha can be 5% or 1%. It depends on what you need. It depends on the experiment design. After that, if we calculate the p-value that is smaller than alpha, then we can reject non-hypothesis. In the other side, if the p-value is greater than or equal to alpha, it means we fail to reject the non-hypothesis. Okay. Interpretation, this is where you interpret in real-world terms the conclusion to the test. The conclusion for a hypothesis test is that you either have enough evidence to show alternative hypothesis is true, or you do not have enough evidence to show that is true. That's true. Okay, and next, confidence interval for the differences between two populations proportion. The confidence interval for the difference in population has the same random variables and proportions and the same assumption as the hypothesis test for two proportions. If you already completed the hypothesis test, then you do not need to state that again. If you haven't completed the hypothesis test, then state the random variables and proportions and state and check the assumptions before completing the confidence interval step. Okay, the first one, find the sample statistics and the confidence interval, the sample proportion, and 1 and 2, P1 height, P2 height, Q1 height, Q2 height. The confidence interval, the formula is P1 minus P2, then minus E, smaller than P1 minus P2, then that's smaller than plus E, And where the E, the formula of E is like this. I know it's very ugly. I know. And statistical interpretation, in general, this look like there is a C% chance that this equation contains the true difference in populations. 3. Real-world interpretation. This is where you state how much more or less the first proportion is from the second proportion. Okay, for example, assume smoking will kill you. Smoking will increase the probability to get cancers. And assume we have two populations. The first one, generally the people in the first population, they smoke maybe 20 or 40 pieces of cigarettes every day. And the second proportion never smoke. We can compare those two populations, and we can say that this is where you state how much or how less the first population is from the second proportion. Okay, let's move to the example 9.1. Hypothesis test for two population proportions. The husbands cheat their wives more than wives cheated than their husbands. It's very interesting statistics. Okay, suppose you take a group of 1,000 randomly selected husbands and find that 231 had cheated on their wives. Suppose in a group of 1,200 randomly selected wives, 176 cheated from their husbands. Okay, sure. Here it didn't define what is cheating. We don't need to define that because we are discussing about the statistics. We are not talking about the society or some family problems. Okay, so we just accept the cheating, but we don't need to define what does it mean about the cheating. Okay. Do the data show the proportion of husbands who cheat on their wives are more than the proportion wives who cheat on their husbands? test at 5% label. Okay, let me explain this. First, state the random variables. Okay, let me. Okay, and here we have husbands. Okay, and we have husbands. The 1,000 randomly selected husbands and find 231 cheated on their wives. And how about the wives? 1,200 wives and 176 were cheating on their husbands. Okay, and now we have data here, and we need to calculate at 5% the confidence interval. Okay, let's move. First, state the random variables and parameters in words. First one, numbers. X1 is the numbers of husbands who cheat on his wife. So we know that X1, that is 231. Number two, the numbers of wives who cheat on her husband. We know that X2, that is 176. And P, proportions of husbands who cheat on his wife. We know that proportion. What does it mean, proportion? P1, that's 1,000 in the denominator, 231 in the numerator, and P2, that is 176 over 1,200. Sure, you may say, oh, this one and this one, the number is completely different. How can you say that? They are different, but no, we need to calculate. And the confidence interval, the alpha level is 0.05. Let's check it. And here, the non-hypothesis, the two proportions are the same. The next, the alternative hypothesis, P1 is greater than P2. You may see, okay, I can understand this one is greater than this one. Undoubtedly, the proportion for husbands are greater. No, it's different. Let me tell you, you cannot calculate by this way because it's about statistics. Okay, let's check it. And three, state and check the assumptions for hypothesis test. Okay, let's move to number 3. A simple random sample of 1,000 responses about cheating from husband is taken. This was stated in the problem as simple random sample of 1,200 responses about cheating from wives is taken. This was stated in the problem. B, the samples are independent. Okay, this is true since the samples involve different genders. C, the properties of the binomial distribution are satisfied in both populations. This is true since there are only two responses. There are a fixed number of trials. Probability of success is the same, and the trials are independent. Okay, let's move to D. The samples distributions of P1 height and P2 height can be approximated in a normal distribution. Thus, X1, 231, N1 minus X1, that's 1000 minus 231, that is 769. And X2, that is 176. Thus, N2 minus N2 minus X2, that is 1024, are all greater than or equal to 5. So both samples distribution of P1 height and P2 height can approximate with normal distribution. No problem. So the assumption is existing. Okay. Question 4. Find the sample statistics, test the statistic and p-value. 5. Conclusion and interpretation. Okay. 4. Sample proportion. N1, that's 1000. N2, 1200. P1 height, 231 over 1000. That is 0.231. Sorry, 0.231. Oh, sorry. P2 height, that is close to 0.1467. And Q1 height, that is 1 minus this one, that is 0.769. On the other hand, Q2 height, that is 0.8533. And pull the sample proportion. Yeah, sure, you can check the formula in the upside. The P bar here, 0.185. And Q is 1 minus that is 0.815. Pull the sample population. And test the statistic. Z score after calculation, we got 5.0704. And got a p-value. 1.988 times 10 to the power of minus 7. It's very small. Very small. Okay. Two sample tests for equality of proportions from continuity correction and alternative hypothesis greater. In the 95% confidence interval, that is this one. And the conclusion, yes, we can reject the non-hypothesis since the p-value that is less than 5%. Do you remember what is the non-hypothesis? What the non-hypothesis is? We assume previously the proportions are equal. Two proportions are equal. Thus, we have the assumption. And 6, interpretation of this enough evidence to show that proportion of husbands having affairs is more affairs. Okay. Then the proportion of wives having affairs, or is a gentle way to say something negative. Okay, having affairs. Okay, okay. And so far, is it okay for everybody? Okay. Okay, how about that? Let's have a 10-minute break. Then later we can calculate those by your hand. Okay, see you later. Let's have a 10-minute break.